Yes, I'm speaking. Can everyone hear me? Okay. Okay, great. Excellent. Okay. So a review from what we did last time. Okay, so we discussed Cartesian products. All right, it's a product of two sets. A times B, it creates a set of n tuples. We discussed truth sets. All right, so a truth set is a set of elements that makes a propositional function true. And then we also discussed some other set operations. We discussed the union of two sets, the intersection of two sets. Okay. We discussed the difference of two sets, A minus B. Okay. So the union of two sets was the set of elements that come from either A, B, or both. The intersection of two sets, A and B, is the set of elements that A and B have in common. They're in both A and B. And the difference of two sets A and B, A minus B, is the set of elements that are in A, but not in B. Okay. We also discussed what the universal set is. Right? A universal set is sort of like our domain. It's a set of all values from which our elements can come from. And we talked about the complement of a set A, right? A bar. Okay, so A bar is all elements in the universal set that are not in A. Okay, so in other words, A bar is the universal set U minus A. Okay. All right, so that basically covers what we discussed last time. Do we have any questions, any homework questions you would like to go over? Okay. Is this from, which section is this from? I see a couple of problems here. Do you want from, all right, from 2.1? Both of you from 2.1. Okay, so 29 and 35 from section 2.1. And then we have some from 2.2 as well. All right. Okay, so let's start with 29. Give me one moment to pull it up. Okay, so the question number 29 is, what is the Cartesian product A times B times C, where A is the set of all airlines, and B and C are both the set of all cities in the United States? Give an example of how this Cartesian product can be used. Okay, so the Cartesian product would be a set whose elements are three tuples, where each three tuple, the first element in each three tuple would be an airline, and the second and third second and third elements would be cities. Okay. So how could that be used? Give an example of how this Cartesian product can be used. You could use that to be like a list of flights that airlines do from one city to another. All right, that would be an example of how that could be used. Like a list of flights, which airlines have flights from which city to which city. Okay. All right. So that's 29. All right. 35. Let's move on to 35 now. 35 asked, how many different elements does A times B have if A has m elements and B has n elements? Okay, so the Cartesian product A times B, what is its cardinality? How many elements will it have? If A has m elements, so the cardinality of A is m, the cardinality of B is n. Okay, so it's just going to be their product, n times n. Okay. All right. Let's see. Let's move on to the next one. Here. Okay. Somebody also asked for 2.1 4C. Okay, so let's do that, and then we'll move on to 2.2. Let's see, 4C. For each of these pairs of sets, determine whether the first is a subset of the second is a subset of the first, or neither is a subset of the other. So C was the set of students studying discrete mathematics. And the second set is the set of students studying data structures. Okay, so that one, neither one is a subset of the other, because you could have students that are in one group but not in the other, and vice versa. So there could be students studying discrete math that are not studying data structures, and you could have students studying data structures that are not studying discrete math. So there might be an overlap. There probably is an overlap. The intersection would not be empty. Oh, okay, wrong question. Never mind. Okay, somebody retracted that question. All right, so let's move on. Let's move on now to section 2.2. Okay, set operations. All right, first question here from 2.2 is 29 C, D, and E. Let me take a look here. All right. So 29 asks us, what can you say about the sets A and B if we know the following? And you're given a bunch of things. So let's look at that. Okay, so 29. What can you say about, in section 2.2, what can you say about the sets A and B if we know that in C you're told A minus B equals A? Okay. All right, well, what does A minus B mean? A minus B is the set of all elements that are in A, but not in B, right? So when we calculate A minus B, we remove from the set A any elements that it shares with B. So if A minus B is equal to A, then that means that A and B don't share any elements. There's no elements that are both in A and in B. Okay, so this, in other words, if A minus B equals to A, then that means A and B, their intersection is empty, so they're disjoint. Okay, so in this one, we can tell that A and B are disjoint. They're disjoint sets. Disjoint sets. Okay. Part D is the intersection of A and B equals to the intersection of B and A. That really doesn't tell us anything about the sets A and B. The intersection, the operation of intersection is commutative. So it doesn't matter which one I write first. It's the same thing. Okay, so this really doesn't tell us anything. All right, and E, A minus B equals B minus A. Okay, what does that tell us about the two sets? All right, well, let's see here. If A minus B equals B minus A, so what does A minus B mean? A minus B is the set of all elements that are in A, but not in B. And B minus A is the set of all elements that are in B, but not in A. So what do you guys think? Let me throw it out to the class. What do you think it means when we say that these two sets are equal? Does anyone have any suggestions for us? Let's see here. I think we have a suggestion. That the two sets are equal. That sounds about right. Does anyone disagree with that? Okay. Yeah, it would mean that the two sets would have to be equal to each other. Okay, because that's the only way that when I remove one from the other, they're the same either way. Okay. All right. So this tells us A has to equal to B. Okay. All right, so that in other words, A minus B and B minus A would just be the empty set. Okay, there'd be nothing left. All right. Okay, so that's 29. Let's move on to the next question. Next, somebody asked about, let's see here, 63 and 64. Let's take a look. All right, so for 63 and 64, you have to read the paragraph before explaining what a fuzzy set is. So let's read that together. Fuzzy sets are used in artificial intelligence. Each element in the universal set U has a degree of membership, right? Which is this is, by the way, similar to fuzzy logic, all right? Which I believe I gave you a homework problem about that back in chapter 1. All right. So each element in the universal set U has a degree of membership, which is a real number between 0 and 1, including 0 and 1. In a fuzzy set S. The fuzzy set S is denoted by listing the elements with their degrees of membership. Elements with 0 degree of membership are not listed because they're not in the set at all. For instance, we write 0.6 Alice, 0.9 Brian, 0.4 Fred, 0.1 Oscar, 0.5 Rita for the set F of famous people to indicate that Alice has a 0.6 degree of membership in F, Brian has 0.9 degree, Fred 0.4, and so on, and Oscar 0.1. Okay, meaning, and Rita is 0.5, meaning the more famous they are, the higher the number is, the closer it is to 1. So that Brian is the most famous and Oscar is the least famous of these people. Also suppose that R is the set of rich people, with R equals 0.4 Alice, 0.8 Brian, 0.2 Fred, 0.9 Oscar, 0.7 Rita. And again, the higher number means the richer they are, the lower number, the less rich they are. Okay, so 63 tells us the complement of a fuzzy set S is the set S bar with the degree of the membership of an element in S bar equal to 1 minus the degree of membership of this element in S. Find F bar, the fuzzy set of people who are not famous, and R bar, the fuzzy set of people who are not rich. Okay, so this is 63. F bar would be what? Okay, so remember, let's write down what F is. F, we were told, is 0.6, instead of writing out the names, I'll just write out letters. 0.6A, 0.9B, 0.4F, 0.1 O, and 0.5 R. Okay, so F bar will be the complement, and we're told the complement is just 1 minus each number. So for 0.6A, 1 minus 0.6 would be 0.4A, 1 minus 0.9 would be 0.1B, then 0.6F, 0.90, 0.5R. Okay, and then it would be the same thing for R bar. I'm not going to do that one. All right, and then 64 tells us the union of two fuzzy sets S and T is the fuzzy set S union T, where the degree of membership of an element in S union T is the maximum of the degrees of membership of this element in S and in T. So find the fuzzy set F union R of rich or famous people. Okay. So again, for this one, we're told that the union is the maximum of the two numbers. Okay. So for Alice, for A, in F, the set of famous people, Alice was 0.6. In the set of rich people, Alice was 0.4. Okay, so in the union, we just write down whichever one is bigger, so 0.6A. And we do the same thing for all the others. Okay, all right, so that would be how you would finish this problem. All right, I'm not going to write them all out. All right, let's see, next question. I think that might be it. Yeah, that's it. Okay. Any other questions? Oh, the exam grades. Yes, I'm sorry about that. Yeah, that's taking me a little longer to grade those online as opposed to in front of me physically. But they're going up soon. They will be going up. I apologize for the delay. Okay. All right. Okay. All right. Any other questions? Will it be on Black? Yes, it is. I will post the grades on Blackboard, and once I've finished doing that, we'll also go over the exam. Okay. Quiz. Yes, there will be another quiz this week on Wednesday. Okay. The next quiz will be on Wednesday. All right. So that quiz at the end of class today, we will discuss what will be on the quiz. All right.
Professor?
Yes.
For the written assignment,
Yes.
can we submit it at any time or just on the
Yes,
given
you
date?
can submit it whenever you like.
Okay.
Okay, just make sure you submit it by the deadline, but you could submit it earlier if you like. That's perfectly fine.
Okay, thank you.
Okay, and again, I remind everyone the written assignment is up on Blackboard now, and you can, as you just asked, you can submit that whenever you like, and the deadline is the last day of class. Okay. When is exam 2 approximately? Yes, the dates on the syllabus are subject to change depending on how fast we move. When is exam? I think I wrote that on the syllabus. When is exam 2? Exam 2 will be when we finish chapter 2. So I would say roughly between 2 to 3 weeks, something like that. Okay, and that's a rough estimate. Okay. We will go over the grading and everything like that once I have all the grades up, and when we go over the exam, we'll discuss the grades. Okay. Okay. As soon as possible. Is my vague answer. But I'm trying to get. I'm gonna try and have them up for you tonight or tomorrow. I will try and have them up for you again. I apologize for the delay. It's a little harder to grade things like this as opposed to having the books in front of me. So it's taking me a little longer. All right. Okay. All right. Okay. All right. I apologize for the delay again. All right. Okay. Let's see what else. Any other questions? Oh, number 32. Somebody wanted to see from 2.2. All right, give me one moment. One moment. Let's pull that up here. Oh, okay. So again, you have for 32, you had to read the short paragraph above describing what symmetric difference is. So you're told the symmetric difference of A and B, denoted by A plus B in a circle like that, is the set containing those elements in either A or B, but not in both A and B. Okay, so it's only those elements that are either in A alone or B alone, but it does not include those elements that A and B share. Okay, so any element in the intersection is out. So you're told to find the symmetric difference of A and B, where A is the set 1, 3, 5, B is the set 1, 2, 3. Okay. All right, so the symmetric difference of these two sets will be the set of elements that are either in A or in B, but not in both. Okay, so 1 is in both, so that's not in the symmetric difference. 3 is in both, so that's not in there. So only 5 and 2 are not in both. So those are in the symmetric difference. So that would be the symmetric difference of A and B. Okay. Okay. Any final questions before we move on? Okay, so let's now continue where we were last time. We were in 2.2, we were discussing set operations. Before we move on from that, I want to discuss generalized unions and generalized intersections. And once we finish that, we can move on to 2.3 and discuss functions. Okay, so we are now still in 2.2, set operations. And we are discussing generalized unions and intersections. Okay. All right, so we previously discussed doing a union or an intersection of two sets, but we can really have a union of multiple sets, not just two sets. We could have as many sets as we like, and same thing with the intersection. We can really discuss the intersection of many sets, okay? So let's start with a definition of what it means to have a union of a collection of sets. So the union of a collection of sets is the set that contains those elements that are members of at least one set in the collection. All right. We use the notation okay, so we use a big union symbol, and we write the union of a sub I from I equals 1 to n, right? For those familiar with summation notation, it's a little similar to summation notation. So this is the union of a sub I from I equals 1 to n. What does that mean? That's equal to the union of the sets a1, a2, a3, etc., all the way up to a sub n. Okay, so meaning I'm plugging in 1 for I, and then I'm plugging in 2 for I and 3 for I all the way up to n. Okay, so I start with the number on the bottom, I equals 1, and I go up to whatever the number on top is n. Okay, so this is the union of the sets a1 through an. Okay, whatever those sets are. All right. We use the notation, this notation, to denote the union of the sets a1 through an, a1, a2, ... through an. Okay. All right. So a union of multiple sets. Here we have an example of a union of n sets. That's a new set, and that's a set of all elements that are in at least one of these sets. Okay, so in other words, it's a combination of all these sets. You take all these sets and put them together, and you create the union. Okay, so any element that appears in at least one of these sets will appear in the union. Okay. All right, let me give you now the definition for the intersection of a collection of sets. The intersection of a collection of sets is the set that contains those elements that are members of all the sets in the collection. Right, so it's really just an extension of what intersection means, right? An intersection of a bunch of sets would be a new set. What elements are in that set? Only those elements that are in each of the sets, right? That all the sets share in common. Okay, so we use the notation right? The intersection of a sub I from I equals 1 to n. So this notation is the intersection of the sets a1 through an. a1, a2, a3, ... all the way up to a sub n. We use that to denote the intersection of the sets a1 through an. Okay. So a union of multiple sets or an intersection of more than multiple sets means exactly what you would think it would mean. Okay, union stays the same. It's just you take all the sets and you combine them to create one big set. Intersection means the same thing again. It's just the set of those elements that all the sets share, that they all have in common. Okay. All right, so let's see an example. Okay. All right. So let's say A sub I, each set A sub I is equal to the following. Its elements are I plus 1, I plus 2, etc., etc. Okay, we'll say that's an infinite set. It keeps going. Okay, so for example, if I was 1, this would be the set 1, then 1 plus 1 would be 2, then 3, then 4, etc., etc. Okay, if I was 4, this would be the set 4, then 4 plus 1, which is 5, then 6, 7, etc., etc. Okay, just as examples. All right. So let's say each set A sub I equals to this, and let's say I starts at 1. So AI equals that, for I equals 1, 2, 3, etc., etc. Okay, so I continues forever. Okay. So the question is, let's see if we can evaluate the following sets. What is the set? What elements? Let's see. Well, let's ask it this way. What is the set that is the union of all these sets? So what is the union of A sub I from going from 1 to n? Okay, what is that equal to? And what is the intersection of all of these sets? So the intersection from I equals 1 to n of A sub I. Okay, what are those two sets? All right, so let's look at this set first, the union. The union from I equals 1 to n of A sub I. Okay, so that's the union of A sub 1, A sub 2, A sub 3, all the way up to A sub n. Okay, well, what is that going to be? Okay, what elements are in A sub 1? A sub 1 is the set 1, 2, 3, etc. A sub 2 is the set 2, 3, 4, etc. A sub 3 is the set 3, 4, 5, etc. Okay. A sub n would be the set n plus 1, n plus 2, etc. Okay. So the union of all these sets will be equal to what? Do we have any suggestions? Okay. Yes, exactly. It will be, as Yasser pointed out, it will be the set of all values of I. In other words, it's the set of everything. We combine everything into one set. So it's just going to be 1, 2, 3, 4, etc., etc. Okay, in other words, it's equal to, which set is that? That's A sub 1. Okay. Yeah, it's A sub 1. All right. What about the intersection? The intersection from I equals 1 to n of A sub I will be the intersection of these sets. Okay. So the intersection is the set of those elements, only those elements that appear in each set. Okay. Which elements are the only elements that appear in each set A sub I? All right. Yeah. Okay, so let's take a look at this. I have a couple of suggestions here in the comments. Okay, remember, what is a sub 1? A sub 1, let me write it out this way. A sub 1 is 1, 2, 3, etc., etc. Okay. A sub 2 starts at 2. That's 2, 3, 4, etc., etc. So 1 is an A sub 1, but it's not an A sub 2, right? So that's not going to be in the intersection. Right? It doesn't appear in every set. What is A sub 3? A sub 3 starts at 3, 3, 4, 5, etc. So 2 is an A sub 2, but not an A sub 3. So that's not in the intersection. That's out as well. Okay, and so on and so forth, all the way up to the last set, A sub n, which is n plus 1, n plus 2, etc. So the only elements, well, let me ask you this. Does the number n, whatever n is, does that appear in A sub 3? It does, right? N is some number greater than 1. So it appears in A sub 3, it appears in A sub 2, and A sub 1, right? So n plus 1, n plus 2, everything after n appears in A sub n, and everything before it. So only these elements in A sub n appear in every set. So the intersection is going to be n plus 1, n plus 2, etc., etc. So the intersection is A sub n. Okay, those are the elements that will appear in every set. Okay. All right. Okay. Oh, just give me one moment here. 1 second. I'm going to be right back. 1 sec. Okay, I'm back. Sorry about that. Okay. 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 Good. Any questions on this so far? Okay. So we can also talk about a union or intersection of sets where we have an infinite number of sets. Okay. So let's say, for example, I wanted to talk about the union of the sets A sub I going from I equals 1 to infinity. Okay. So that would be a union of an infinite number of sets. Right? That would be A1 union with A2, etc., etc. And I can also do the same thing with intersection. Okay, and it's the same idea. The union of all these sets would be the set of all elements that appear in all of the sets. And the intersection would be just the set of those elements that appear in every set. Meaning, in other words, the set of elements that the sets have in common. Okay. So I can do another example in an infinite number of sets. Let's say for this example that each set A sub I equals to 1, 2, 3, all the way up to I. Okay. For I equals 1, 2, 3. All right. So here, instead of starting at I, I'm starting at 1 and ending at I. Okay, for each set. Okay. So now let's look at the union from I equals 1 to infinity of A sub I. What would this set be? Okay. So this set would be, well, before we do that, let's actually write out what this would be as like this. A1 union A2 union, dot, dot, dot. Okay, so that would continue forever. Let's take a moment and look at each set. What is A sub 1? If I equals to 1, then A sub 1 is just the set whose only element is 1. A sub 2 will be 1, comma 2. A sub 3 will be 1, 2, 3, and so on and so forth. Okay? So what would the union of all these sets be? All right? If I combine all these sets into one big set, I'm going to have the set that contains the numbers 1, 2, 3, 4, 5, 6, 7, etc., etc. Right? It's going on forever. So in other words, that's z plus. That would be the set of positive integers. Okay. What about the intersection of these sets from I equals 1 to infinity? Right? A1, intersection A2, intersection dot, dot, dot. Okay. We have a suggestion that the intersection would be the empty set. Let's see if that pans out. Okay. So we do the intersection of these sets. Looking at these, I wrote out the first three, but these sets go on forever. What element can you tell me will be in all of the sets? Is there any element that appears in all the sets? The number 1, yeah. So the intersection would be the set that contains the number 1, since that's the only element that will appear in every set. Okay. Yeah, excellent. Okay. All right, so that's it for generalized unions and intersections. All right, any final questions on that? All right. Okay, so no, we're not finished yet. All right, we're now going to move on to functions in section 2.3. We're going to begin our discussion of functions today. Okay. All right. Okay. So we're going to start. Functions are used throughout mathematics and throughout a bunch of other different areas as well. A bunch of different disciplines. All right. I'm sure almost all of you are familiar with functions, if not all of you. We're going to start this section by giving the formal definition of what a function is, and we're going to define functions using sets. Okay. All right, so first a little bit of an introduction. All right, so in many instances, we assign to each element of a set a particular element of a second set. Okay, which may or may not be the same as the first. So, which may be the same as the first. As the first set. All right. Anytime we do this, we call this assignment a function. So this assignment is what we call a function. Okay. All right. So what is a function? A function is where we have two sets. We'll call them set A and set B, and we'll give those two sets names in a moment. And the function assigns elements from one set to elements in the other set. Okay. You can also think of functions as a sort of like an input and output machine, right? You take an element from one set, you input it in, and the function is a rule that tells you what your output will be. Right? It assigns to your input some output, okay, from the second set. All right, so let me give you now the formal definition of what a set is. Excuse me, what a function is. All right. Okay. Let's say we have two sets, A and B. So let A and B be non-empty sets. A function f, right? So a function, we'll call our function f, from A to B. Okay. Now, as I'm sure you already know, we don't have to use the letter f for a function, but generally we refer to a function with the letter f. Okay, so a function f from A to B is an assignment of exactly one element of B to each element of A. Okay, stressing the words exactly one in each. Okay, so it's a function f from the set A to the set B is an assignment of exactly one element of B to each element of A. All right. We write f of little lowercase a equals lowercase b if that little b is the unique element of the set B, is the unique element of the set B assigned by the function f. All right, I'm writing func as short for function, assigned by the function f to the element A of the set A, okay, A of A. All right. If f is a function from A to B, we write this. F followed by a colon, followed by an A with an arrow pointing to B, okay? So this is not logic, so that's not an implication, that's not a conditional statement. That means f is a function from set A to set B, okay? Okay. All right, and functions are also sometimes called by other names in different areas in mathematics. They're also sometimes called mappings or transformations, okay? So functions are called mappings, and they're also called transformations. Okay, so what's an example of what a function could look like? Let's draw it out using a Venn diagram. Okay, so I'm going to draw an example of a function using a Venn diagram. Okay, so here is a set A represented by this circle. Here's a set B represented by this circle. Okay, let's say the elements in set A are A1, A2, and A3. And the elements in set B are B1, B2, and B3. Okay, my function f is a function from the set A to the set B. So I have to assign elements from B to elements in A, okay? So let's say A1 is assigned B2. I'll show the assignment by drawing an arrow. Let's say A2 is assigned B1 and A3 is assigned B3. Okay. So I show the assignment by drawing arrows here. So I could write this as follows. F of A1 means the element in B assigned to A1 by the function would be B2. F of A2 is equal to B1, and F of A3 is equal to B3. Okay, so this here would be an example of a function. Okay, another example. Actually, before I give you another example, let me give you another definition here. I want to define a few more terms, and then we'll do some more examples. Okay. All right, so we're going to define a few more terms. So for the next definition, does anyone know or remember what the set A and what the set B are called? One-to-one, we'll get to that soon, or maybe if not today, then next time. Okay, first let's deal with the definitions here. So set A is called the domain. That is correct. Set B is not called the range. Does anyone know what set B is called? We'll define what the range is soon. Okay, so set B is actually something called the codomain. I don't know if anyone has heard that term before. We will define, the range is important. We will define that soon. But first we need to define the codomain. All right. So if a function, and again, FUNC is short for function. Excuse me, if f is a function from A to B, we say that A is the domain of f. It's the domain of our function. Okay. And B is the codomain of f. So A is our domain, B is our codomain. All right. If f of A equals to B, right, where A is from the set A, B is from the set B. Okay, A and B also have special names. So we say that B is the image of A. And A is a pre-image of B. Okay, so A, the set of elements from A are called images. Okay, and B would be called a pre-image. I reverse that. Sorry, A are the pre-image. A is the pre-image. B is the image. All right. Okay. So going back to the previous example that I wrote here. Okay, I could say, well, continuing that example from above. Okay. So from that example from above, let's continue that example. The domain is the set A. Okay. What elements are in the domain? A1, A2, and A3. What elements are in the codomain? Well, the codomain is the set B. The elements in the codomain are B1, B2, and B3. Okay. If f of A1 we said equals to B2, then that means B2 is an image of A1, and A1 is a pre-image of B2. Yeah, this is the same example from above. Okay. All right. So what is the range? All right, let me give you the definition for the range now. The range of f is the set of all images of elements of A. Okay, and let me explain what that means. Okay, so let's do a couple of examples here where we'll sort of demonstrate these different definitions here. Okay. Okay. First of all, let's look at this thing here. Let's say I have a set A and a set B. A has 3 elements, A1, A2, A3. B has 2 elements, B1 and B2. Okay. A1 is assigned B1, A2 is assigned B2, A3 is not assigned anything from B. First question, is this thing a function? Yes or no? Is this a function? Okay. All right. So we got a couple of yeses. Let's go back to the definition for a moment. For a function. Oops, scrolling back. What did we say in the definition? Let A and B be non-empty sets. A function f from A to B is an assignment of exactly one element of B to each element of A. Is each element of A have an assignment? In this example, no. There is an element of A that does not have an assignment, A3. So therefore, this thing is not a function. This is what we would call a partial function, but I'm not going to get into that right now. Okay, so based on the definition we gave before, this is not a function, okay, because A3 is in the domain, but it has no assignment. No, it has no image in B. Okay. So I cannot have if something is a function, then I cannot have in my domain elements that do not have images. Okay, so for this thing to be a function, A3 would have to not be in the domain. All right. Okay. All right. Next example. No. Okay. All right, let's say next example, I have 2 sets. A has 2 elements, A1 and A2. B has 3 elements, B1, B2, B3. Okay, let's say A1 is assigned 2 elements from B, B1 and B2. And A2 is assigned 1 element, B3. Is this a function? Right, okay, so this is not a function. Why not? Again, let's go back to the definition. So this is not a function. Again, we go back to the definition. What did we say before in the definition of a function? It's a function from A to B is an assignment of exactly 1 element of B to each element of A. Okay, in this particular example, I have 2 elements in B assigned to an element in A. Okay, so f of A1 equals B1 and B2. Okay, so if I have one input that can give me more than one output, right? One element in the domain that is assigned to more than one element in the codomain, then it's not a function. So this is not a function because A1 has more than one image. Okay, so again, it's not a function. Okay. All right. Next example. Let's say I have a set A, a set B. Okay. A has 3 elements, A1, A2, A3. B has 2 elements, B1 and B2. Okay. So f of A1 equals B1 and f of A2 equals B1. And then f of A3 equals B2. Okay. So in this particular example, f of A1 equals f of A2. Is this a function? Here the answer is yes. Okay, this is still a function. Okay, so I can have 2 elements in my domain that are assigned the same element from the codomain. That's fine. This thing is still a function. Okay, so this is a function. All right, that's fine. We just would say that it's not one-to-one, but we'll discuss one-to-one soon. Hopefully we'll get to that today. If not, we'll discuss it next time. Okay, so this is a function. All right, one more example here. Let's see. Okay. Is this one a function? So here, A1 is assigned B1, A2 is assigned B2, B3 is not assigned anything. Is this a function? And here again, the answer is yes, okay? We don't require that everything in B be assigned to some element in A. So not everything in the codomain has to be assigned to something in the domain, okay? So this is a function. It's just not what we would say it's not onto, but again, we'll discuss onto together with one-to-one later on, okay? So here, f of A1 equals B1, f of A2 equals B2, and there's nothing I can plug into the function to get B3. This is a function, okay? So there can be elements in my codomain that are not assigned elements in the domain. All right. In this particular example, the domain, I'll write D for domain, okay? Now let me just actually write it out. The domain here is the set A. What elements are in the domain? A1 and A2. What elements are in my codomain? Well, the codomain is the set B. The elements in my codomain are B1, B2, and B3, okay? What elements are in the range? Okay. So remember, let me scroll back to the definition we gave for range before. I'm just going to scroll back for a moment. What was the definition of range? We said the range of F is the set of all images of elements of A. Okay, it was the set of all images. So looking back at this example, B1 and B2 are images. B3 is not an image, right? So B1 and B2 are images. B3 is not an image. So the range of this function would be the set containing B1 and B2. All right. Okay. So the range is really a subset of the codomain. Okay, so the range is a subset of the codomain. Okay, it's the set of only those elements in the codomain that are images, that have pre-images. Okay. All right, any questions on any of these definitions? I see we have a couple of comments here. Exactly one element, right? Vertical. We'll get to one-to-one and onto soon. Yes, and this is the difference between codomain and range. Okay. All right, so we'll get to one-to-one and onto pretty soon. If we don't get to it today, then we'll get to it. Like as I said, we'll get to it next time. Okay. Oh, we're not finished yet. Okay. Okay. All right. Okay, so we could have different examples of functions. So far, I've given you functions using Venn diagrams as my examples. I could also give you functions in different ways. So first of all, if I give you a function, I have to tell you what the domain and the codomain are. Okay, so if I want my function to be from the set of integers to the set of integers, I would write it this way. Okay, so whenever I write this, this means that my domain is here. That's the first one. That tells me the domain. So the domain is the set of integers. And the codomain is also the set of integers. Okay, so I have a function. I plug in an integer. I get out an integer. Okay, so first I have to tell you the domain and the codomain. And next I have to tell you what the function does. So the function f of x takes in numbers x. And what is the output? Well, it could be anything. So let's say it's x squared plus 1. Okay. This would be an example of a function where the domain and the codomain are the set of integers. So I'm allowed to plug in 1. If I plug in 1 into this function, what is its image? The image would be 1 squared plus 1, which is 2. Okay, so this function f of x equals x squared plus 1 gives me the rule. How do I assign elements from the domain to the codomain? Okay, what if I plug in -3? That's also an integer, so I'm allowed to plug that in. That's in the domain. That would be -3 squared plus 1. That would be 9 plus 1, which is 10. Okay. Since I told you the domain is the set of integers, I'm not allowed to plug in anything that is not an integer. So I would not be allowed to plug in a half, right? I can't do that. Half is not, 1/2 is not in the domain. Okay. For this function, are there elements in the codomain that are not in the range? Can anybody come up with an element that is in the codomain of this function, but it's not in the range? In other words, can you find me an element that has no pre-image? Any suggestions? If you want, I could also rephrase the question. In other words, are there numbers that this function cannot be equal to that are in my codomain? Can you find me some number that my function can't be equal to that is in the codomain? 3, yeah, I think that works. Let's write that out. All right. 3 is in the codomain because it's an integer, but I believe it's not in the range, right? X squared plus 1. If I wanted that to be equal to 3, okay, what would x have to be? Well, -1 minus 1. X squared would have to be 2. So x would have to be the square root of 2, which is not an integer, right? That's not an integer. All right, so that's not in my domain, okay? So 3 is in the codomain. It's an integer. It's in the codomain, but it's not in the range because there is no integer, there's no element in the domain that I could plug into my function that would give me 3. Okay, so 3 is in the codomain, but not in the range of this function. Okay. All right. That could change if I change my domain and my codomain. So if I, for example, if I change the domain and codomain to the set of real numbers, then that would change. Then 3 would be in the range and in the codomain, because the square root of 2 would be in the domain, right? The square root of 2 is a real number. Okay. Any questions on that? Okay. Let's discuss now combining functions in different ways to create new functions. All right. So definition. Let f1 and f2 be functions from a set A to the set of real numbers. Okay. We can add two functions together to create a new function, and we can also multiply two functions to create a new function. Okay, so then f1 plus f2 and f1 times f2 are also functions from A to R, defined for all elements x in the set A by the following. Right? So the function f1 plus f2 of x is just the sum of the two functions. So it's just f1 of x plus f2 of x, whatever those two numbers are. And same thing for the product. f1 times f2 of x, that function is equal to the product of f1 of x and f2 of x, whatever those two numbers are. So, for example, let's say f1 is a function from the set of real numbers to the set of real numbers, and f2 is also a function from R to R. Okay. f1 of x, let's say, is equal to x squared, and let's say f2 of x is equal to x minus x squared. What is their sum and what is their product? Well, f1 plus f2 of x will be f1 of x plus f2 of x. Okay, so this is a new function that's going to be equal to x squared plus x minus x squared, which is just x, right? X squared minus x squared is 0. And their product, f1 times f2 of x, would just be the product of the two functions, which would be x squared times x minus x squared, which is x cubed minus x to the fourth. Okay. Okay. Yes, that is correct. When we multiply or add functions, as we said in the definition, the domain and the range will stay the same. Okay. All right. Oh, can I go up a tiny bit? Sure. All right. Okay. Any questions on any of this? All right. So if there's no questions, we will stop here for today. Okay. As I mentioned, we're going to have a quiz on Wednesday. We'll do it at the end of class on Blackboard. All right. The topics that it will cover, it's going to cover everything we did in 2.1 and everything we did in 2.2, including what we did today on section 2.2. Okay. So 2.1 and 2.2. All right. Anything we did in 2.3 today at the beginning of class, at the end of class, will not be on the quiz. All right. Any questions on that? How many questions? I'm not sure at the moment. I don't remember, but I will give you enough time at the end of class. Okay. So again, the quiz will be 2.1 and 2.2. All right. It will not cover anything in 2.3, just 2.1 and 2.2. Okay. All right. Okay, everybody. Let's end here today. Let's take the attendance. And I will see everybody on Wednesday. Take care, everybody. Okay, yeah, nothing from 2.3 from today. Only the things that we did from today on 2.2. Okay, so only 2.1 and 2.2, nothing from 2.3. Okay, everybody, I'm going to assume I got everybody. I'm going to head out. Take care, everybody. And have a good day.